Before GPT, the dominant language model was just counting which words appear after which other words. It was called Ngrams. For 20 years, it was the best you could do. It felt embarrassingly simple. It worked embarrassingly well, and it's still in your phone's keyboard right now. Today, what an Ngram is, why the math is literally just counting divided by counting, the one problem that quietly haunted the whole approach, sparsity, and why RNNs, and then transformers finally displaced them. Last video, Shannon gave us the metric, entropy, perplexity, 1.3 bits. Now we build the machines those metrics evaluate. And the classical answer, from about 1980 until 2010, was Ngrams. Approximate that impossible P of next word given all previous words by looking only at the last 2 or 3. The puzzle. If Ngrams are just counting divided by counting, why is there an entire subfield about them? Why do textbooks spend chapters on NGRAM smoothing? The answer, sparsity. Most word sequences never appear in any corpus, ever. And your model has to say something about them anyway. That is the whole game. Today's 3 beats. First, the anatomy. Unigrams, bigrams, trigrams. Maximum likelihood estimate. Count over total. Second, sparsity and smoothing. Add 1. Back off. Kneser-Ney. The technology that made Ngrams actually work. Third, where Ngrams still live, why phone keyboards love them, and why RNNs. Then transformers displace them for anything requiring long context. Beat 1. Anatomy. A unigram model just uses the probability of each word alone. A bigram model conditions on the one previous word. A trigram model conditions on the 2 previous words. The N in Ngram is the size of the window. Bigger window means more context, more accuracy, and worse sparsity. That trade-off is the whole story. How do you get the probabilities? Maximum likelihood estimate. Count how many times the bigram appears. Divide by how many times the first word appears. P of sat given cat equals count of cat sat divided by count of cat. That's it. That's the whole learning algorithm of a classical language model. Ratio of 2 counts. To score a whole sentence, apply the chain rule from L4E6. Product of bigram probabilities across the sentence, or in log space, sum of log probabilities. Every bigram model in production computes exactly this. Simple, fast, straightforward. Beat 2. Sparsity. Consider trigrams. If your vocabulary is 50,000 words, there are 50,000 cubed possible trigrams. 125 trillion combinations. Nowhere near enough text on Earth to see all of them. So the count of most trigrams is 0, which makes the MLE 0, which makes the whole sentence probability 0, which kills your model. The fix. Smoothing. The dumbest version, add 1 to every count. Every possible Ngram gets at least 1 imaginary occurrence. So nothing has probability 0. It's called Laplace smoothing or add 1. It's the training wheels. It works, barely, and it's provably suboptimal. But it demonstrates the whole idea. Redistribute probability mass from seen events to unseen ones. The real deal, Kneser-Ney. The gold standard Ngram smoothing. Instead of a naive add 1, Kneser-Ney backs off from higher order Ngrams to lower order ones. And, this is the clever part, uses how many contexts a word appears in, not just its raw frequency. York appears a lot, but almost always after new. So P of York as a standalone continuation is lower than raw counts suggest. Chen and Goodman's 1998 tutorial made this the industry standard. Beat 3. Where Ngrams still live. Phone keyboards. Autocomplete. Predictive text. Places where the context is short, 1 or 2 previous words, and speed matters more than long-range coherence. A 3-gram table in a phone keyboard is fast, tiny in memory, and good enough. Every major mobile keyboard shipped one for over a decade. Some still do. But Ngrams have hard limits. The window is fixed. A trigram model can't use anything from 4 words ago, and it certainly can't remember what happened 3 paragraphs back. So they fail on anything requiring long-range coherence, pronoun resolution, thematic tracking, discourse, the whole L3 upper stack, which is why RNNs, recurrent networks replaced them in the 2010s. Then transformers replaced RNNs. Zoom out. 20 years of NLP research was mostly making n-grams smarter. Smoothing, interpolation, clustering, class-based models, cache models. Every trick was a variation on compensate for sparsity in this specific way. Then RNN and transformers made most of that irrelevant. But the perplexity metric is Shannon's. The chain rule is L4E6. The counting is n-grams. Even neural LMs still stand on this foundation. 3 takeaways before the quiz. 1. N-grams are just counting. MLE equals count of the n-gram over count of its prefix. That's the training. 2. Sparsity kills raw counts. Smoothing, from add 1 to Kneser-Ney, is what made n-grams usable at all. 3. Fixed window is the hard limit. Neural LMs, one on long context, but n-grams still ship in your phone. Quiz 1. What's the maximum likelihood estimate for the bigram probability P of sat given cat? A count of sat divided by count of cat. B count of cat, sat divided by count of cat. C count of cat divided by count of sat. Or D 1 over vocabulary size. B. Count of the bigram divided by count of the prefix. That's the whole training procedure for a classical language model. Ratio of 2 counts. Every bigram model in production computes exactly this, and nothing more. Quiz 2. Why do NGRAM models need smoothing? A. To make training faster. B. To compress the model. C. Because most possible n-grams never appear in any corpus. Or D. Because MLE is illegal. C. Sparsity. With a 50,000-word vocabulary, you have over 100 trillion possible trigrams, and no corpus will ever cover all of them. Unseen n-grams have MLE 0, which kills sentence probability. Smoothing redistributes mass so nothing is 0. Kneser-Ney is the gold standard. Quiz 3. What's the fundamental limitation of NGRAM language models? A. They can't compute probabilities. B. The context window is fixed, so no long-range dependencies. C. They only work in English. Or D. They can't run on phones. B. Fixed window. A trigram model looks at 2 words back and no further. Pronoun resolution 3 sentences later. Thematic tracking across paragraphs. All invisible. That's the whole reason RNNs, and then transformers displace them for anything requiring long context. Back to the puzzle. N-grams became an entire subfield because the raw idea, count divided by count, hits sparsity immediately, and every smoothing trick was fighting that ghost. The fixed window is the ceiling. Neural models eventually broke through. But the underlying math, chain rule, perplexity, log space, is exactly what neural LMs still use. Next video, hidden Markov models. Because sometimes the sequence you care about is hidden behind the one you observe. Like a part of speech tag behind a word. Next time, hidden Markov models. The classical way to reason about a sequence when the thing you care about isn't directly visible. Part of speech tags behind words, phonemes behind sound frames. 9 minutes, real math. Hit subscribe.